And welcome to this session, Teaching Analytics in Chemistry, which is a new addition to our academic webinar series. And I'm happy to present this to you for the first time. And it's also good to see such a mixed audience. Many of you are using JMP Pro and the recent version, but we also have some new users or no JMP users yet. But maybe tomorrow, let's see. And that's my goal, to inspire you and to show you what JMP can do for you for teaching analytics in chemistry. So this is the abstract of this session you probably remember from your registration. And what can you expect from the session today? So it's maybe not a surprise that you will see some of JMP. But what I really want to share with you are best practices and tips and resources to teach analytics in chemistry. And all the time when I say chemistry, I mean chemical sciences and also chemical engineering. And at the end of the session today, I will show you some easy steps to get started, to get access to the resources, to the software, and to a lot of useful material. But first of all, I would like to inspire you and to show you what's available. This will not be done by slides or by writing formulas on a whiteboard. What I will do, I will show you a broad mix of applications. Applications which I think are all interesting for a chemist, and they show skills which are really relevant to solve problems in chemistry. So today, this won't be a deep dive, neither into how to use JMP, a software training, nor into any specific method today, but we will get an overview about a range of applications, and that's what's planned for the next hour. So let me start with a case. Why a case? Yeah, maybe students are also asking you, why should I also learn JMP and use JMP? And I already have Excel and I'm using R and other packages. One answer could be that JMP is a real problem-solving tool also used in industry. And how can you prove this? How can you engage the students? Maybe by showing a case study, a customer success from industry like this one. So this is about Novomer, a chemistry company based in Massachusetts. And their objective was to put carbon emission from power plants in industry to productive use. In this case, producing plastics used in packaging and coatings rather than CO2 escaping into the atmosphere. So here you see a bit about the journey Novomer did using JMP. So they started with 35 potential factors. So it was a lot about screening at the beginning, root cause analysis, and they used JMP for data mining. And a result from this first phase was a subset of 10 factors. And then they took these 10 factors into an experiment to learn about the process. And with only 21 runs, 21 measurements, they were able to determine which 3 factors were really important and significant for their process. So these were monomer CAT or CAT, water, and temperature. And because they used a definitive screening design, which is a 3-level design, as we will see later, they were also able to see that there was some curvature going on. So a quadratic relationship between the yield. They wanted to maximize, of course, and the yield was poor in the past. So that was the main goal here. And a surprise for them was this curved relationship. So this was against everything they expected and subject matter experts proposed. And we can also look at the end result with this JMP data set. So here you see the response measurements, and we also see the 10 process settings, our factors. And you can also go back to the design where you see that this was a definitive screening design they used, both for screening, but also for the optimization step to find the best settings. So by looking at the final result, you see the relationships between yield and our top 3 factors. And we see that we have a linear relationship for water, for instance, and we see the curvature for temperature. So we have 3 factors in place. We have 5 different effects going on, 5 active effects for this process. So the 3 main effects, but also an interaction between monomer cut and temperature. So you can see this by changing one factor. You see that the other factor from this product is also changing its slope. So that's the interaction. And we also see the quadratic effect on temperature. And then it's an easy step on the profiler here to find the best settings. And the solution was to use low monomer cut and a low water and this setting for temperature, getting to their solution to solve the problem. And this development led to recognition by MIT's Technology Review magazine as one of the 50 most innovative companies in 2011. And then it has been sold to a spin-off called Saudi Aramco for $100 million. So this shows that using a data analytics and also a data collection package wisely and efficiently can really, really matter. So you can read more about this success story if you look at our customer success stories, and you can get access to this one. And there's also a statement here you can listen to and read more about that story if you want to know this. And how to get access. So these are your takeaways from today's session. So if you are not covered by a JMP license, you can access the JMP 30 days trial at this URL here. And this would be needed to open this journal. We will also share with you together with the recorded session in our academic webinar library at this link here. And this journal has all the links, the URLs you can then click for further reading and to study some additional content. If you are new to JMP, I will leave this for your reference and studies. If you think you want to see what JMP is and where it's coming from, there's a short video. You can also look at the application areas and then move into any of these areas if you're interested in more quality related methods or more predictive modeling, data mining, machine learning methods. Just click on these areas and then you will get access to white papers and use cases and applications and a lot of other information. And customer stories, so they are also nice. So for chemistry, so you can also choose customer stories, and then by industry, chemistry. And then you see also the Novomer case study, but also many other case studies from the chemical industry where JMP was used to solve their problems. Yeah, have a look there, why to teach using JMP. You will see this later, so I will just skip this information here and not read it. So I'm using JMP Pro on a Mac, and there are also some other products, and there's also more information about other JMP products, but it's typically a no-brainer. So with the JMP site license, which is called a JMP Academic Suite, you always get access to JMP Pro on campus level, department level, or professor or course level. And this is the typical license, academic license used for teaching. Just look for JMP Academic Suite. If you want to get more information, pricing information, anything, please get in touch. academic@jmp.com is our email address. So let me start with the first application. And for some good reasons, this is design of experiments. So if you are not used to designing experiments, you may ask, why to do this? Because this is a much better, meaning more efficient, more effective approach than just guessing, trial and error, or one factor at a time. What we still see in industry, but also taught in several courses. This DOE is the only way to learn about cause and effect, and not only about correlation, and to try out something new, driving in innovation. For that, also DOE, designing experiments, is the most efficient approach. Why to teach it? Because it really matters in industry. So 2 years ago, Imperial College designed their Center for Doctoral Training and their curriculum for PhD student education. And they started a survey in the chemical industry. They asked almost 30 companies in the UK, what are the skills you require? What should we teach in our CDT? And guess, the number one skill which was mentioned was design of experiments. 72% of the companies required that skill. So this is really relevant for problem solving, for chemists and engineers. And if you look at curricula at universities, you see that statistics courses are cut down more and more, and they typically end at a simple linear regression. There are some more data science, machine learning courses replacing them, but this is a different focus. This is more about prediction rather than understanding or optimizing a process. So a DOE course could be really a nice vehicle also to add some more problem-solving skills or statistical thinking to your curriculum. So summing up, this would really close a gap between what the industry needs and what's currently taught at universities. So let us look at a first example. So this is a data set, a sample data set. You can also make this smaller. This is a sample data set you can also find on the sample data library in JMP. And this is a designed experiment, as you can see here. So this is created using the custom designer. And the problem here is that we want to maximize the yield and understand the relationships between our 5 continuous factors and this yield column, which is called percent reacted. And if we look at the distributions of our columns, our variables here, you see that this is a two-level design, and you also see the distribution of our response. We could go back and see how this design was created. So for that, I just click on this green triangle running this script, which is stored after a design to the design table. So you can always go back and see how was this done. So using the custom designer, we specified the response. There's only one response, but you can also have multiple responses. We set the 5 continuous factors with their low and high values. There are no constraints in this case. And we have the model. And this is also called a model-driven design because we tell the designer what we want to learn. We want to learn about the main effects, maybe to do some screening, but we also want to learn about interactions in this case. And taking all of this into account, the design tool suggests a design, in this case with 20 runs. You can also set the number of runs. It was set to 20. And then this is the test plan, 20 runs you have to carry out and you have to measure your response. Quite interesting is that you can look at the quality about the outcome, what you can learn from this experiment before you actually run the experiment. So here you see the power, for instance, and the power is interesting because this tells you how likely it is to confirm an active effect. So if concentration would be really active and have an effect on percent reacted, with this experiment, we would have an 81% chance to confirm this. And other way, we would also have a 19% chance to miss concentration in our result as an active effect. So that would be the bad side, the mistake. And with this here, so if you want to learn about everything, and if you want to get everything, the straightforward approach would be to test for all combinations. And all combinations, that means hundreds of runs because you have to combine all the factor combinations. In this case, we only have a reduced set of runs, not a full factorial design, but a reduced set. And this reduction in budget and effort needed has a price to pay. And this is one part of this price to pay, some smearing or correlation between our effects we are studying here. So these are the 5 main effects versus the main effects. So this here is all white except the diagonal, but every effect is correlated with each other by 100%, so that's fine. But all other main effect combinations are uncorrelated. That's nice. But for other combinations like this one, so this is a correlation between the main effect catalyst, which is here on the left, and the interaction feed rate times stir rate, which is above. So at this crossing point, we have a correlation. It's not that big, but there will be some aliasing or smearing. So that means that an effect on the response caused by one effect can show up as caused by another effect. And you cannot tell from this experiment which one is really causing what you see on the response. So this is called aliasing, or if they are totally correlated, we also talk about confounding. Yeah, and this is what you don't want to have, but some aliasing is acceptable in many cases, especially if you just do some screening design. So it depends. And the design tool controls this wisely and also tells you about it before you run the experiment. So you will know. Yeah, and then you take the measurements and you run this experiment, and the data table still remembers what's the goal, what you want to learn. So that's what we specified on the model, the effects, the parameters we want to estimate from this experiment. And because we have our response measured now, the experiment is done, I can build the model, yeah, and then look at the profiler again. And here we see our 5 continuous factors, and we see the response percent reacted. We see the lower limit, which is 70%. And this also reminds us that we want to maximize. So higher response values have a higher desirability. Yeah, I can also go up and and look at all the effects, and they are sorted by p-value. So the least significant one is at the bottom. You see the p-value here, and I can remove this effect from our model. And the recommendation is to do this one by one. And this one is a main effect, which is also used on another more significant effect. So let's keep this and let's move on here and remove effect by effect. So typically higher order effects first, but now I can also remove the main effect stir rate. It does not seem to have a significant effect. You see also here the slope is flat. Yeah, so this is not really changing anything on our response. So let's forget about it. Yeah, and you remove also this one here. And then we have 5 effects left for these 3 factors. And then you can also look into interactions, for instance, and see how any changes change your response. And the optimization is a simple step looking for the maximum desirability, and you get this solution: high catalyst, high temperature, and low concentration. But all relationships are linear because we are just looking at main effects and interactions, but no quadratic or cubic effects in this example. Remember, this took us 20 runs. And we used the custom designer for this, allowing the highest flexibility you can find in the market, even for solving problems using DOE. There's a more modern approach for screening, and this is called a definitive screening design. And this is a definitive screening design for the same problem. So we have the same factors and we have percent reacted, but this design, as you see here on the column headers, is a 3-level design. And this is pretty smart. So I can also show you those here. So this is the response again, the factors, and we also have the diagnostics. And here you see, oh, wow, we have no correlation at all in this region. So between main effects and also not between main effects and interactions, and also not with cubic quadratic terms, sorry. So this is a nice feature. And if you fit the model, and there's also a very efficient way to do this using the fit definitive screening platform, a fitting platform, as soon as the experiment was done. And I take this, the result, I build a model using fit model, and you directly get to this result here. So maybe we can also forget about, well, let's keep a feed rate in here. Or let's remove it. So now we again have 5 effects. And the difference is that in some cases, a definitive screening design can also detect curvature, and then you can also use it for optimization. So not just do the screening, so determine these 3 factors here, but also optimize, because now it's not all linear anymore, but we also found some curvature, and not just curvature, but we found that we have curvature for this factor here, concentration. Yeah, and remember, this was done by 13 runs only. So that means with less effort, we can learn more. And that's pretty cool. And if you want to know where you can use a definitive screening design, it's not for all situations, but in many situations, it's very efficient and very useful. And you can also refer to a blog post or online information where this question is discussed. Another example, still DOE, is about mixtures. So here, some factors are not independent, but they typically sum up, like portions, ingredients in a mixture. They sum up to a constant. And here we also have some additional factors which are called process variables. And this is the mixture experiment. And here we see the distributions again, and we have these 3 mixture factors which always sum up to 100%, 10% on the first run, 10% plus 80 plus 10%, 100%. So if we look at the distributions, we can see that if we select a setting on our categorical process variables, we see that everything else is balanced. So that's a nice feature, some good news. And if I select a setting on a mixture, so here we see if I choose the low mil3 on the third stage, the third milling stage, a low value, I can still select low, mid, or high on the other 2 stages. But if I do 80% on the third stage, for the other 2, there are just 10% left in order to sum up to 100%. So they are not independent. Also, by clicking here, look at our response, which is reflectivity in this example. And again, we want to maximize. So the higher is better. Can you see what's better? Yeah, so high milling or a lot of milling done on the third step seems to be much better than a low setting here, or even a mid setting. So that's insightful, and we can learn a lot without building any model, but we can also build a model easily. So this is a Tannery plot, by the way, which is a typical visualization of mixtures. So this is also available in JMP. And if you build a model, I just build it quickly, and you look at the profiler again. So these are our mixtures. And if I increase one setting, you see that the others have to decrease to compensate, to keep the sum constant. Yeah, same here. So they are not independent anymore. And this is also shown on the profiler. The last example here is an example where our response is not just a single value, but a function. Yeah, and here we see the functions for different batches. Yeah, and these are functions of a sizing response over time. Yeah, and time is also not synchronous, not the same measurements, the same time measurements for all batches, but they are different. And this batch down here, so this is our golden curve where we want to be. So drop very quickly and then stay in the green region in our target zone. Yeah, so this is our target, and how to find the best settings for our four factors to get as close to this target as possible. This can be done by using functional DOE. So this platform has a workbench for data prep and pre-processing. Here I just loaded the target for this example. So then you see the black dots, these are the measurements, but the red curves, these are the models using B-splines. So now we take these models and we still have the target curve down here. And based on these models, we do a decomposition into functional principal components. And this was done here. So there's one mean. So this is the average function for all batches. And then we add a certain portion of this component to the average. More or less of this eigenfunction number one principal component. And if we add no component, we just get something which is very similar to the mean. We can also subtract this component, or we can add this component, yielding to such a function. And this tells us how much of this component we should add to see a certain curve as the response. But this is typically not what you're primarily interested in. You want to know how to set your process to get as close as possible to the target function here. So this is size over time, and this can be changed by changing any of our factors. And again, it's the same process, maximize desirability. And this shows us the solution, how to set our process to get to this function, which is quite close to what we set as our target function. So this is using functional principal components. And you can also have functions as inputs, as factors. And for that, we have a special modeling platform called Functional Data Explorer in JMP Pro. And if you have functions as inputs, we call this functional machine learning. And this is supported by that platform. So for each application, I have some suggestions how to learn more. So for DOE, we have this workshop organized, hosted by the RSC, a chemistry world. It's called Smarter Experimentation for Chemists, and you can access videos and homework and data sets And this teaches you the basics of experimentations with examples from chemistry. And we also have this new offering here. So this is called our academic suite for CDTs, or master programs for doctoral training. And the offering we developed together with Imperial College in London, this is tailored for chemists and chemistry, chemical engineering. And the core part here is a 2-day training course where you get the delivery of the course, you get all the course content, you get some train the trainer, so that you get also independent in teaching this course, and a lot of other supporting material. If you're interested in this, you can also look at this webinar here we did together with Imperial College. This is our CDT offering for chemistry. Okay, some more applications and examples. So a broad application area is, of course, interactive visualizations, basic analyses. And this is typically done for two purposes. One is to get a first understanding about your data set and your variables. So this is called exploratory data analysis, what's always recommended before you run any analysis. And by doing this, by looking at your data, you may also see some data problems or things you should correct, you should fix before you analyze your data. Now, of course, there are also some other tools especially designed for looking at messy data and cleaning up messy data. So looking at outliers, missing values, suspicious patterns. Yeah, but also by visualizing your data, you can see a lot, and that's always a good idea to start. So here we have a manufacturing process for a chemical drug, and we see the yield, and the yield is a percentage, and we want to understand which of our process settings, and there are many categorical and also continuous settings for our process, which of them are really important. So we start to do some data mining and look for some patterns and clues. So this is really fun also for students to play the detective and study a new data set. And one basic tool for visualizations is the graph builder. Yeah, so we can look at the yield. Where are we now? And you see the yield as a dot plot. Yeah, and you can also look at this by a histogram or a contour plot or a box plot. Yeah, I can also press the shift key and just add the data points and now have both the dot plot and the box plot. So to see where we are, and the green ones are good batches, and everything below 80%, the dots are red. So these are defects and batches which had to be removed. So this is about visualization. You could have maybe some statistics like a 5-number summary, but it's more for visualizing your data. I can also add the vessel size here. So now we see the box plots, but for 3 different groups, categories. So these are the different vessel sizes. I can also take this carbamate amount, which is continuous, and drop it on the axis. So now we see many, many box plots, but this is more for a scatter plot, where I can also add a smoother. I can fit less or more to my data. Yeah, so I switch this to a line to see the trend. And now I'm also interested in, what about vessel size? Do we have the same trend for different sizes? So I can look at separate lines, but I can also overlay. And this looks interesting because here we see that the relationship between yield and carbamate amount depends on vessel size. So the red one, for instance, has a negative slope, and the other two have a positive slope. So this is an interaction between carbamate amount and vessel size. You can find out by exploring and visualizing your data. Another basic platform is distribution. So I can look at yield again. Maybe if you just have one variable, you may want to have this as a horizontal layout. And now I can use the red triangle to dig deeper, maybe check normality using a normal quantile plot. Or I can fit a normal distribution to my data and see if this is a good fit or not. Yeah, so here I have goodness of fit, another red triangle. Yeah, let me remove this again. Yeah, so this is also a very rich platform and always recommended for exploring your variables. And it's especially useful if you look at multiple variables, but I only want to see the histograms. Yeah, and now I can select all the bad ones, all the bad batches. So these are the ones below 80% yield. And I can directly see the relationship with vessel size. I cannot explain everything by a single predictor or setting, but I can just explore my predictors and, for instance, also see that lower carbamate amount may lead to more rejected batches. Now you can spend some time on exploring your data just using the distribution platform and clicking around. The next step would be to look at two variables at a time. So what about yield versus vessel size? This would be, there's an overview here. You can cheat and see, we will get into a one-way ANOVA scenario. But I can also look at yield versus carbamate amount, which is this one here. And then we have the same platform, fit Y by X. But for the continuous case, you can look at means and ANOVA. The ANOVA tells us there's a difference, and then you can compare the groups to see where the differences are concerning the mean. And on the other side, we look at a continuous by continuous case. And here we get a scatter plot and totally different options. So this is more about fitting, so we can add a line or non-parametric density contours. So this is a totally different scenario because the data types are different, but it's the same platform. And there's also multivariate platform, which allows you to look at correlation between your continuous factors, and using this, so we can also look at outliers. And if you think that this one here above this control limit, this one here, You can also see this here. And if you think it's really outside of our main data cloud, you can always hide and exclude it and then get rid of this suspicious data point for some time, maybe for the next analysis. Now I get it back in. And there's also another shortcut analysis if you're interested in modeling. So what is really driving our yield here? You can look at a predictor screening. So I'm interested in yield, that's my response. And then I put all the X's, categorical and continuous, into this X box and click OK. And then I get this ranking here. And the most important one seems to be vessel size according to this analysis. And the least important one is amine supplier. We could spend hours just on visualizing, exploring our data. And here are some other links and resources. And one of them is this online course. It's a free course, Statistical Thinking. And here you see also that we have different modules. And one module is about exploratory data analysis. And this is about preparing your data, cleaning your data, and visualizing your data when you start with a new data set. There are also other modules about other applications, including quality and also DOE, which are also highly recommended. And we also have course material freely available for you. So if you want to teach introductory statistics or regression modeling analysis, choose that type of course and then see which guides and case studies and demonstrators, lab activities, and books can support you. There's no green field if you want to use JMP for teaching. So the third application is about multivariate analysis. And here we are building a model using partial least squares. And the journal tells us why this is used in chemistry so often, because it can really help you when ordinary least squares doesn't help anymore. PLS can be a nice platform for you. And here are some use cases. If you have more variables than observations, more X's, if you have highly correlated X's, or if you have hundreds, a large number of X variables and maybe also several responses, Y variables. And this is the example I want to share with you. So this is about drug discovery. And new drugs are developed from chemicals that are biologically active. And because testing a compound for biological activity is expensive, chemists typically attempt to predict biological activity from other cheaper chemical measurements. So here we see exactly this for two studies, a first study and a second study. And each record presents a peptide chain of 5 amino acids. And these 5 acids are coded by letter in this column OBS/NAM. So that's the chain of amino acids. And the response here is RAI, R-A-I. And this response is highly skewed, as you can see here. And by looking at this, it's highly skewed. You also see the outliers here. So by looking at this, you may get the idea, better use the log transform of this variable. And getting this is really easy. So you just click here, new formula column transform log base 10, and then you get a variable which looks much more symmetric and well behaved. And this log version is then used for this analysis. So exploring the predictors, I just run these scripts here. So looking at the predictors, yeah, it's the same story. You see all the X variables, and oops, there's nothing to cause any real concern here, but exploring predictors, looking at distributions, always a good idea. Yeah, and the goal was here to develop a model from the first study and then also deploy the model for the second study. And the modeling, let me exclude the second study. So now we can do the modeling for the first study only. And this modeling can be done using fit model. And because we have so many access and just 15 observations, I choose partial least squares. Yeah, and the log version here is my response, and the predictors are added as model effects. Now we only have one response, so I don't need this here, and then I run this. I can also choose the other simples method. It's the same basically for a single response. I don't do any validation, and I only want to have 2 factors to start with. And then I click go. And then it's quite easy to see. There's a lot of information, but it's quite interesting to see that for only 2 factors, so these 2 factors explain almost 30% of our access. So there's a lot of correlation between the access, and there's some latent structure, and with 2 factors we can explain 30% of the access and almost all the variation of our response. And from our variables, 6 of them are contributing to these factors, significantly contributing to these factors. And then we can look at the scores here, and we also see the variation explained again. And then there's a lot of information, a lot of additional information you can add here. So you can look at the loadings. So how do the effects, the axis, load on our 2 factors? I can also look at a scatter plot matrix for the loadings. I don't have the time to go into the details here. And as always, we also make it very easy to check diagnostics, different versions of diagnostics, and that can really help also to detect non-normality, autocorrelation, non-constant variance, everything which can really, signal some problems for the model fit. And here are 2 important ways why an X can be useful. It can explain the latent structure very well, and this is called the VIP. And I can look at the variable importance plot, and everything above 0.8 is considered important, explaining the latent structure. So VIP, this stands for variable importance for the projection. This is about the projection. But it's also important if a variable is important for the modeling as the regression coefficient. And here we see both dimensions. So we see the coefficients, and we also see the VIP. So everything above this dotted line is interesting, is important for the projection, and everything with a significant coefficient is important for the modeling for the prediction. And then what you typically do here is, you pick a subset, only the important axis, and then you can make a model for that, for the reduced set. And if I choose the same settings, we see that in this case, this variation explained dropped a bit, but here we are doing much better explaining the underlying structure, correlation structure on our axis. If I take this model and save the prediction formula from the last model, just using the subset, and then look all my data, so I can get an actual by predicted plot. So the actual log response is this one, and the predicted is this one. But I want to have this by study. So here I can do this or this, and now I switch to align. And now we see that for this actual by predicted plot, we see that for the first study, the model looks quite good because this is on close to the diagonal of this graph. But for the second model, for the second study, we really have some bias here. And that's maybe a good point to discuss also in class. And you can have any student assignment now combining both studies for modeling, looking into an increased number of factors, not just 2 factors. And you can also apply cross-validation to determine the best number of factors. But also note that dynamic visualization in JMP can really help students to make some sound modeling decisions. I don't have the time to look into process and quality tools. So this would be about measurement systems analysis, but the example is about process stability using control charts and capability. So this is from the Six Sigma application arena, and also quite useful and powerful in chemistry. And I just want to refer you to these resources here, where you can learn more about this application area, process and quality tools. And there's also a module in the STIPS, the statistical thinking course, I really recommend. And the more you get more resources you can explore on your own, but the more I just wanted to mention is shown by the JMP starter. So we looked into DOE today, and we also looked into multivariate analysis using partial least squares. But here you can see that there's much more in JMP, for instance, on predictive modeling, machine learning, specialized modeling, including nonlinear fitting, time series analysis, and a lot more. So I will close now by suggesting these 3 steps. If you want to get started, the 3 steps I recommend are the first, get ready, talk to us. Get ready and understand what JMP can do for you. Discuss all the questions you have. Ask for personalized demos. Tell us about your needs and allow us to share the best practices and resources for your learning objectives. The second step is try it yourself. If you don't have access to JMP, get a trial version. Maybe also look at the DOE workshop to learn about DOE. And you can also access JMP Pro in the cloud, because this is accessible through a browser if you register for the statistical thinking course. And then the third step is, deploy a license and use it in teaching. And using this link, you can get some information about our licensing. But then that should be straightforward. And then, there's no greenfield. So check our course material library and see what's useful for you, for your courses, all the different types of resources we have there. And then some options to stay connected using opt-in, register on the JMP user community, join thousands of other users and learn from them. And also look at our academic industry network if you're interested to collaborate with industry partners.